Okay, how's it going, everyone? This is attempt number 2 because the first one, I did it all and then it didn't save and then I was sad. So I did like a whole hour of explaining of the problems, but I don't know why it just didn't save. I really hope this time it works. So, welcome everyone. This is just a solutions or going through the problems. We're not gonna actually get the answers. I just want to walk you guys through the steps on how to solve these problems from the first exam. And so, just a little preface to this. I hope by now, after going through the exam once, you guys have an idea more or less of what to expect for the next exam in terms of the structure, the logistics, how we do it, especially with this online situation. And we once we have that idea, it's really useful because then when we take the next exam, we're more focused on the content than like the structure, if any of that gets in the way. um, and what to expect when you take a test, and how I give exams, what's on the exams. For this one, we covered a few topics. So let me start sharing my screen. And so you're going to see text in it because this is what I wrote in the last time I did it and it didn't go through. But the first problem, I mean, when you guys take the exams, it randomizes it for everyone. So you don't start off with the same problem that your other friend does. The values are different. You get different numbers. So even if you start with the same problem, two people aren't going to have the same answer for the same problem because it changes per person. But what you can see is that more or less you'll see like one or two problems that are the same from the practice exam or from the practice test, from the practice quizzes or practice exam. And take that into account for next exam. The whole thing isn't going to be just a carbon copy of itself. You're going to have similar problems, one taken from the quiz, one maybe from the practice quiz or practice test, and the rest of them are going to be similar. So we had this problem, and then from as I went through the one I took, because I wanted to solve these for all of us, this became the second problem. So this one's with kinematics. You had This one's like a mixture of the first two problems from the practice exam. The two-dimensional kinematics problem, the car coming off and the thing shooting. This is like both of them combined into one. So it's just understanding the concepts from there. And that's one thing I want you guys to kind of take away. Like, it's not about just memorizing a process of generic equations. It's understanding the steps that you have to take to get to the answer. If you guys understand the concept behind each problem, then you can connect that to any other problem that has that same concept applied, even if it's different. This one was about the tensions on a box. This problem relates to the rock climber. So if you understood the concept, then you can see how this relates to it. If you're like, how did this relate to anything we had to do? Then that's a lack of the understanding of the concept. And so if you understood the concept, it's easier to connect. And that's what I want you guys to get, like, understand the concepts and the logistics for how you approach these problems. These problems with forces are all about free body diagrams. So getting the box, getting all the vector components, and then figuring out which ones are in the y-axis, which ones are in the x-axis, getting two equations, and then solving from there. This problem is the same thing, a little simpler. You didn't have to explain anything, just matching. And this is just something you guys already saw. And then this problem was, okay, so when you see it for the first time, of course, it doesn't seem simpler, but this is only half the work of a problem like this right here, because you're only focused on one dimension, and that dimension is the x-axis, and finding the acceleration in the x. So you only have to get the x component, and then you use Newton's first law, which is right here, and you can solve for it, instead of having to focus on two dimensions, which takes more effort. And then this last problem, definitely the hardest. Whoo, definitely. I don't know how you guys did it, but I hope that you guys were able to garner all that intellect to get the right answer, because yeah, I struggled with this one too. You'll see when I get to it, I'm gonna be so stuck. I'm like, what's the right answer? Is it all of the above? No, I'm kidding. Okay, I'm just kidding though. This is just free points. The other thing I wanted to mention is, you see how I have names of people on here? Uh, I'm not trying to play favoritism. Like, I like putting people's names on here because I want to make this exam yours. Like, I want to make it customize. I want to customize it to the class. I'll make you guys feel special throughout the session, the summer session. Each exam's gonna have new people in there, and the goal is to try to get as many people in, put their names on these exams. Unfortunately, it's hard to get everyone with 35 people, because unless I like put 2, 3 people in one question. But I really want to, because you guys deserve the recognition. You guys are in this class, and hopefully this brings some laughter, joy, or any of that stuff. But yeah, it's not like I pick people like because of favoritism. Like, it's just, I remember people and I pick them, and then next time I'll remember a few other people. I'm like, okay, these people I'll put, and then for the final I'll put more people. But yeah, what allows me to put the most people is the last question, because I can like do more multiple choice options and then see who's gonna burn the book, who has the highest desire to burn it. And of course, if you can choose anyone, the answer would be me and then one of you guys. But I think, to be honest, it might be like a tie between all of the options right here, between Danielle, Tinja, Sarah, Brandon, and Daniel. How dare you? No, I'm kidding. No, like, honestly, trust me, I know the feeling. When I was taking a class I hate, I'm like, I want to burn the book. But yeah, um, the struggle's real. Like, you guys are going through this 8-week course. It's so fast paced and demanding. And I really do appreciate like everything you guys have put forth, honestly, because like, if I'm being honest, like, you guys being in this class says a lot about your character. It says a lot about your goals and your ambitions to persevere, because you can easily take this class another semester and maybe just fall a little bit behind, and but you guys are taking this during your free time, and you have something in mind, a goal, something you need to endeavor to, and that's either go and get transferred to a different school, to a 4-year college, get into some type of graduate program, or for other reasons that get you to your end goal, or to at least a better position in your educational and your actual career that you want to get. And that speaks highly of you guys, because you guys have so much freaking potential. I almost used the other word. And you guys do. I can acknowledge that, your maturity, everything. And like, especially summer classes, like, it's always like really motivated individuals like all of you, and it means a lot. And I'm super honored to be teaching you guys, or at least guiding you all, because as you guys see, you guys have to learn a lot of this on your own. So I try to be accessible to a certain extent, of course, to help out. But thank you for everything you do, honestly. Like, I can recognize it and appreciate it. So you guys are awesome. Okay. So with that being said, this first problem, we already worked on this one from the practice quiz. Essentially, your slant is like this. So if you see the y and the x-axis, you want to make your coordinate system like that. Sorry, like something like that. The reason you do that, and the reason why you don't do your coordinate system like this, x and y here, is simply because if you do it like this, the only force in the y-axis is weight. In the x-axis, there's nothing directly in the x-axis. The normal force and the frictional force, you would have to break these two down into their x and y components. But with the green coordinate system, you have the frictional force and the normal force both exactly in the y and in the x-axis. So the only force you would have to break down would be gravity, the weight. And that's easier to break one force down as opposed to two. That's why we set the coordinate system like that, because it helps us simplify the math. And that's the whole situation with these problems, finding the easiest way to get to a certain answer. Okay, so there we go. the problem reads, at least what it's asking for, it's what is the acceleration down the slope? If Lena, for Lena, if there is a coefficient of kinetic friction, whatever. So it's already giving you the direction. You just need to give the magnitude, the acceleration going down the slope. So with that logical step, I would prefer making the direction of motion positive. You don't have to, but if you don't, once you get your answer, you're only putting the value, the magnitude, because you already know it's going down the slope. If you make this positive, your answer is negative, that means the acceleration is in this direction. So that's why it's negative. And so by doing that, you can start to break down your vectors. So if you zoom in right here, I hope this time it does record. If it doesn't, I'm gonna cry and I'm just gonna be like, sorry, you guys, I'm gonna have to record this another day when my computer ain't glitching out or when Zoom. But if you zoom in, sorry, sidetracked. Breaking your X and your Y and your X component, you can see the Y component is parallel to this, your X is parallel to that, and that's all you wanna do. And just remember the magnitude, the actual weight with the Y component gives you the 19 degrees, the same angle that you have right here. So you break down your Y and your X component, and you can write these two down. You can write Y is adjacent, so it's cosine, and X is sine. So you can write these two down. The normal force, technically, we don't have the normal force, but we can already assume that it's going to be the Y component of the weight. And that's just because logically, in the Y component, the skier isn't going up or down. But we will get that from this equation. So we're jumping the gun. Frictional force, we know the equation for that is normal force times the mu coefficient. So we need to know the normal force to find frictional force, which is kind of like the stepping stone and ladders of the ladder of how we're gonna progress through this problem. So the first thing we wanna do, get the Y, the blue components, which are the Y components, and write an equation for them. So the net force in the Y direction, so the Y component of the weights is negative because I'm choosing downwards to be negative and upwards to be positive from that slant. So that's why I have a negative sign right here and there's a positive right here. And all of that is equal to 0 because, of course, there is no acceleration in the Y direction. So 0. The way you want to think about it is just isolate the axis. And if the skier goes up or down, then there's motion. So then there would be acceleration. But in this case, there isn't because the skier doesn't go up or down. It stays on that same plane, doesn't go up or lower with respect to that plane that the skier is going down. So 0. Then from here, you can kind of already tell what's going to happen. The weight, if you put it on the other side, and the Y component is going to be equal to the normal force. So that's going to give us our normal force, which is the weight in the Y. That's all the Y-axis does. If we move on to the X, let's write down the two forces, this one and this one. So I'm just going to underline them, this one and this one. We put them here. Friction is negative. Gravity in the X-axis is positive. That's what's causing the skier to go down. And that is not equal to 0. It's equal to MA because there is an acceleration in that X direction because the skier is actually going down. So there's motion and we can assume there's some acceleration. If it turns out there isn't, we'll end up getting an acceleration is equal to 0 from all of this work. So we have this down. We know friction is equal to mu times the normal force. And if we already know the normal force is equal to the weight in the Y-axis and we know the component, how to break it down, we're going to plug that into there and multiply that times mu. So before we do that, if we look at this step, sorry, I have it all written down. I hope this isn't confusing. Hopefully walking you through makes some sense. And I keep checking to make sure that this thing is recording. So the weight in the X minus the frictional force is equal to MA. So it's just this equation. We're going to plug in what the weight in the X equals to. It's W sine of 19 minus friction is mu, normal force times mu, and that's equal to that. If we go down, we can plug in what W is equal to is mass times G times sine minus mass times G times cosine. So the normal force is this right here. bam. So we can get that down here and replace it with the normal force. And the mu goes afterwards, is multiplied, and that's what the mu is equal to. So make sure to include that. And then make that equal to mass times acceleration. Like you're just copying this equation down here and plugging in what you know. So it starts to expand. One thing you'll notice is that there's an m for each term. So you can cancel that out. So you don't even need to know the mass. All you need to know is g, which is 9.8. And that's it. Everything else is given, the values, and we can solve for a, which is the acceleration in the x direction. So that's how we can solve this problem. The rest is just plugging it into your calculator to determine a. And that's how you solve this problem. Just breaking it down into these steps always helps. The next problem, like I mentioned, it relies on the concept of kinematics, like those equations in the x and in the y. And so one thing I do have to mention first and foremost is that just because the diagram shows that it hits here, that doesn't mean that the height, the h, is going to be higher than the 20 meters. As you can see what I wrote right here, drawing is not to scale. So that's to indicate that it's not to scale. Let the math give you the answer. The reason why, I mean, like I need to draw a trajectory just to show that it's moving. But as I mentioned, each person gets different values. So depending on values you get, maybe the trajectory might end up lower, might end up here, it might end up over here, or it might even end up higher, like somewhere over here. And that's all depending on the values you get. So you don't want to rely on that. And that's why I put drawing not to scale, because it's not. Don't assume it should be bigger. Let the math do the talking. And that's how, this diagram is just as a reference to show you what's happening. But aside from that, you just want to use your kinematic equations, plug in your initial conditions, and then find the answer from there. So what I like to do is begin with the y equations, because we're trying to find the height, which is a y value. And so if we work backwards, for me, that just makes the most sense. So you would get this equation right here. Y is equal to y naught plus vy naught times t plus 1/2 ay t squared. Of course, ay is equal to negative g, because negative is pointing downwards. If we already made that assumption, that down is negative, up is positive, and then right is positive, and left is negative in the x-axis. So we replace everything. Our y is equal to h, because that's the final height we're trying to find. Our initial y is, you're in top 20 meters, so that's what you would put. B of y, you wouldn't put the 15 meters. You would need to put the component in the y-axis, which is just the magnitude times the trig function. The y is opposite of the angle, so that's why it's sine of 23. But we don't know the time, so we leave that like that. And then we have the 1/2 and negative g, which is negative 9.8 times t squared. So what you can see is, in order to find the height, we need to find the t's. So that means we need the other equation. Why did I use this equation? So for this problem, if you're not explicitly given the final velocity, you don't know the final velocity unless it's a specific case, like where the object reaches its maximum height. But here we don't know if that's a maximum height. We're just finding it once it hits a certain distance on a wall. And so people might, the misconception is that the velocity final is 0 because it hit the ground and then stopped. But you need the velocity at the moment it's impacting. So like, how hard did you feel it hit you? Like, how fast did it hit the wall? Not after it hit and it stopped. That's after the problem. You want to find that final velocity as it hits, not afterwards. That's already too late. So we don't have that information. When you don't have the final velocity, you want to resort to those first equations, this long equation that only has the initial velocity included in the equation. And you're going to use this for both the y and the x. So once we use this y one, we found out that we need to find time. So then we'll use the x equation, this one right here. And all we have to do now is plug in our values as well for the x direction. It's a little simpler because we already know the x, I was going to say g, the acceleration in the x axis, which is 0, because there's no acceleration in the x. And you would plug this in here too, which is just 15 times cosine of 23 delicious degrees instead of sine of 23 delicious degrees. Oh, we just plug that in. And this is kind of what you get. Sorry for I crossed things out because that's what I did earlier. So 20, and then the initial is 0. This is this whole thing right here times time. And because this term cancels out, since there's 0 acceleration in the x-axis, you don't have to include it. So what you do is you cancel this whole thing out. You just divide it to the other side. So you end up with this. So if you plug this into your calculator, we can get the time. And we needed the time, right? So we just plug that into the blue equation and voila, we can find our h. So that's what you do. You have these two equations, replace one into the other, completo. And that's how you do that problem. So hopefully that helps. Pause at any time if you guys need to look at certain steps. Also, comment below if you guys do have any questions and I'll answer them. These videos are all private, unlisted, so only you guys can see them. So any comments you put, no one else is going to see except for your classmates. Might help them. But if you want more, like, not to put things like on blast, you guys can also email me too. Feel free. Sorry, I had a burp. I'm disgusting. So the next question, saying what is the mass of the box? So what is this mass of this green box if two ropes with tension T1 and T2 are holding it up? So you're only given the tension for one rope, which is T1, 52.21 newtons. T2 is not given. So when you are not given this force, that means we're going to have to find it a different way. That means we have two unknowns. We don't know the mass. We don't know tension too. So we're going to need two equations. And so just like the rock climber, I always forget, what is it? The rock climber problem, we had two unknowns. We didn't know the force from the legs and the tension of the rope. So same thing, but this one's actually a little bit easier because you'll see as we go through this. So what I did here is I first had to figure out what directions the actual tensions pointed towards. So I drew an arrow for the green one for T2, but I'm drawing one for T1. The box is here and gravity pulls down, right? So the tensions have to pull outwards because if they're pulling downwards, everything's just gonna fall. There's nothing countering gravity. So the tensions are pulling upwards to keep gravity from bringing the box down. So the arrows are important to get proper component directions. And so once I do that, if we focus on T2, I drew this darker red line to start the right triangle. So it's pointing up because I started at the tail and then go up and then you go to the other side. So maybe it's this way for you guys or maybe not. Yeah, it is this way. Go this way. And now you've completed this triangle right there. And so by doing that, you get the angle, 45 degrees. And you can see that T2y, the component in the y-axis for tension 2, is opposite and T2x is adjacent. So that helps us a little bit. And I'm color coordinating. So red vectors are in the y, blue in the x. And so we look at this triangle now. And then same thing, just make a right triangle with respect to where the angle is at. That's the easiest way to see this. Go up, connect it. So you start at the tail and you just follow that right triangle. And once you finish one axis, draw the little arrow, then go to the next one, little arrow. And that indicates where the vector components should be pointing like perfectly, never fails. So after doing this, you can see that the tensions in the y component, they're both pointing upwards. So they're both positive. For the x, they're pointing in opposite directions. So I'm going to make T2x positive and T1x negative. So then when you look at this equation, that's what I did. Essentially, we get the net force. There's only two forces in the x, T2x minus T1x, because it's pointing in the other way. And this problem, the whole thing in all axes and even the fourth dimension, nothing is moving. So the net force has to equal to 0. There's no acceleration. So you draw these two, you write these two forces on. I mean, you could draw them artistically. which I do not have any of that, as you can see by my chicken scratches. So you draw the two forces components, make that equal to 0. And that's in blue, blue. And now you look at the red, and the net force in the y direction, there's 3 forces, 1, 2, 3. The 2 tensions are positive, but the weight points in the other direction, so that's going to be negative. You had to have that intuition for the negative direction, because I mean, if there's no weight, then the box would just float. There's no reason for there to be tension, and that way it would just pull it up, and then you would have acceleration. But because gravity is pulling down, you need to include that. And so we did. Now we have our 2 equations. So now let's move on to the x equation. And what I'm going to do is just write the components for T2x and T1x. These are adjacent to the angle, both of these. So they're going to use cosine, but make sure you put 45 degrees for T2 and 15 degrees for T1. So T2, the magnitude of it, times cosine of 45, and minus T1 cosine because it's pointing the other way. So then you plug all of that in. And the beautiful thing about this problem is we're given one tension. So we're given T1. So you can plug this in. For my case, it's 52.1 newtons. You can just plug it in. And then you can just rearrange everything to solve for T2. We need to know what T2 is. So with this, you can find it. Once you plug this in, you divide cosine to the other side. So you divide cosine over here. So you can isolate T2 and you can get this answer. You can plug it into your calculator and get a value, but I'm not going to do that. I just wanted to show you guys how to get there. We will move on to the next equation now, because what we're trying to do is solve for the mass. So you always have to keep your eye on the objective, because if the objective is not to solve for T2, then that's not the end of the problem. Sometimes we did so much work for one thing that we forget, and we're like, oh, this is the answer. And that happens a lot. And it sucks because I'm like, oh, you guys had the right idea. Like, you guys just slightly forgot the objective. So we move on to the y equations. There's 3 forces. There's tension 1y pointing up, tension T2y pointing up, and gravity pointing down. So again, we're going to replace it with what the vector components are, keeping the proper sign. And what we do here is we move mg to the other side to make it positive. And now we have everything here, which we know. We know that tension 1 is 52.1 times sine of 15. T2 is right here. So all we have to do is plug it into there and then times sine of 15. And we know all of that. So you can just plug it into our calculator. And the last thing we would have to do is divide G. So I divided G. So then we can get our answer in terms of just mass, which is all of that right there. Boop, boop. And you can just solve for that and you're done. Okay. This next problem, a little simpler. It's the same thing that we did in the practice, but instead it's just like slightly different variations of how the forces are acting on you. In this case, it's like, what if you brake or if you accelerate really fast, which scenario corresponds to A and B? And so you didn't really need to explain, you just had to match it. A is when your head goes back. Just kind of think of what happens. So let me do it like that. I can't lift anything up. So, okay. So I'm driving along, boop, 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 and then I'm like on my phone. I'm like, like a car is coming. Like I'm getting closer to a car, so I have to brake really fast. And when I brake really fast, like if you have something on your seat, it's gonna like slide forward, right? The same thing with your head, like like your head just like slams forward, forward, not back. I just like that. And that's when you brake really fast because your car is moving. So at first, you guys both have the same speed. You and your car are moving forward at the same speed. When you brake, your car slows down first, but you're not attached fully to your car, only like your body. Your head is dangling free. So it doesn't feel the change in velocity until the change goes through your body and reaches your neck. And if you had your head tied up to your car seat, you would all move at the same speed. But because this is like disconnected from that, it feels the force later because it still has the same velocity it did before you pressed on the brakes. And so that's why your head moves forward, because it has a faster velocity than the car that already slowed down. What's keeping your head from going forward is that you have a seatbelt on and keeps your body to the car. The other scenario, when you go back, that's when you accelerate really fast. And that's just the opposite effect. When you accelerate really fast, your car travels. So you guys both have the same speed at first, and then your car gains a lot more speed than what your head has. Your head has the older speed, the slower speed. So that's why your head trails behind. You're like, ah, and then that happens. So hopefully that kind of explained. You didn't need to, for these things, you don't really need to get technical with him. Like, I just want a logistical explanation, nothing too fancy. But yeah, hopefully that kind of helps with that. Okay, this next problem. So what I mentioned about this one being like half the work, and of course it might be hard because like, how do you even approach this problem if you don't even know how to start it? Like, of course it's going to be hard. But if you just look like in terms of looking at the work that you have to do for this one in comparison to the other problem, the one with tensions, it's like half the work you have to do. And the reason for that is because this problem is asking, so you're ignoring friction. There's no friction, so there is no force pointing opposite of the motion of this block or box, and you just want to find what the acceleration is in the horizontal direction as somebody pulls it 25 newtons, 35 degrees from the horizontal. You can think of it like a backpack and you're pulling it at an angle because you don't pull it perfectly horizontal. You may be wondering, why doesn't it come up? That's because the component in the y direction isn't stronger than the weight of gravity. So even though you're pulling it up, it's not sufficient to get it lifted up, but it is sufficient to move it left and right because there's no acceleration pointing opposite of the motion in the x direction. So if you find the component in the x direction, if you get the 25 newtons and you get the x component, then you found the force in the x direction, and you can use Newton's first law to plug it into here and relate it to the acceleration. And all you would have to do is divide the mass and you can find your acceleration. The component for the x direction is 25 newtons times cosine of 35 because it's adjacent. These 35 delicious degrees, you just plug it in there. Make sure you guys plug it in degrees and not in radians, because then you would get the wrong answer. So I hope that didn't happen to any of you guys. And lastly, you would see this like that. And that's how you do this problem. That's all. You only focus on one axis. You don't have to worry about the y because you're only finding the acceleration and you only have one unknown. You don't have more than one unknown. And then lastly, the hardest problem: who's most likely to burn their physics textbook after this exam? I'm pretty sure it's all of you guys. Like after this, I'm sure like, it's brutal. Like it was a tough test because aside from the concepts and all of that, just online learning, and especially because this class is already like a hybrid course as it is, because you guys have to like self-teach yourself a lot of this. Like I try to provide a lot of resources, not a lot, but more resources than normal. But even that, like, it's a lot to consume, and having to kind of understand the structure of this course and how each section can help you learn. And even though it's going really fast, like even by this point, like trying to figure out a way that can help you understand the concepts or learn the material at an efficient rate is still something that is ongoing for most of you, for all of us. And so it's tough, but I want to thank you guys for your amazing effort and for just pushing forth. Honestly, like, use me as a resource. Try to get all of this graded. I should have finished this long time ago, but because I had to redo this, hopefully it's still recording. But yeah, the struggle. But anyways, that's it for the content. If you guys have any questions, comment down below, email me, whatever you like. But thank you so much for all you do. Honestly, like I know I keep repeating it, but I do appreciate it like a lot. You guys I might not display my appreciation, but I do appreciate it. So thank you all for being so freaking delicious. You guys freaking rock. And I'll see you guys in a little bit because it's almost Tuesday. And so I'm going to be seeing you in a few hours. Yeah. Okay. Bye, everyone. Be safe. Stay safe and do all that fun stuff. I'm gonna stop the recording now. So see you guys in the morning. Bye.